Hello, my name is Samantha Ballard, and today I will be discussing my talk on coastal land-air-sea interaction, CLASI, satellite observations for 4D boundary layer monitoring. I would like to acknowledge my co-authors and colleagues from Rasmus and SeaStars, as well as the numerous universities involved in CLASI. Overview of what I'll be discussing today. First, I'll introduce a 4D monitoring system used during CLASI. Then I will introduce the SAR imagery acquired during CLASI for the CLASI pilot in 2016, as well as the follow-up field experiment in 2021. I'll discuss SAR-derived air-sea products, wind, waves, air-sea fluxes, and I will also discuss SAR in reference to in situ observations from buoys, drones, boats, etc., and the incorporation of SAR and modeling output from COAMPS and LES. The combination of remote sensing spatial data sets from satellites, land-based radar, etc., with in situ temporal observations from buoys, ships, weather balloons, aircraft, land towers, and drones are used to improve modeling from the Navy's COAMPS model, as well as LES modeling. The combination of remote sensing in situ observations and modeling creates a 4D suite of land, air, sea measurements used to improve coastal predictions. This can be represented through field experiments like CLASI. The CLASI pilot was a 2-week experiment conducted in 2016, where 29 SAR images were acquired over Monterey Bay, California. There were some limitations with the 2016 pilot, and there was a clear need for improvement and more data. Therefore, a follow-up experiment was planned in 2021. Improvements needed in terms of the satellite imagery include more SAR imagery with higher temporal sampling, and the images were acquired at dawn and dusk only. There was also limited in situ validation during the pilot. Only beach towers were available, and there was a clear need for more in situ air-sea measurements from buoys, which was improved in the 2021 campaign. Therefore, we went back to Monterey during 2021 for the new and improved CLASI-West field campaign, during which we acquired 223 SAR images from 4 different satellites over a 4-month period from June to end of September 2021. SAR images were acquired every day, with the exception of about 4 days, and 1 to 3 SAR images per day were acquired with high temporal variability. Also, we have co-located buoy measurements as well, which is a great addition to the CLASI pilot dataset. X-band SAR satellites Cosmos SkyMed, as well as TerraSAR X SAR images were acquired in both the CLASI pilot and the CLASI 2021 field experiment. Cosmos SkyMed has 5 by 5 meter resolution, and TerraSAR X has 3 by 3 meter spatial resolution. We are also very excited to have 2 new satellite constellations, ICEYE, developed by a Finnish company, and Capella Space, which is a US-based company. ICEYE developed its own synthetic aperture radar sensor suitable for microsatellites under 100 kilograms in weight with 3 by 3 meter spatial resolution. Capella Space successfully launched the first operational US SAR satellite, Capella 2, which was launched in 2021, right before the CLASI field campaign. Capella produces the world's highest spatial resolution commercial SAR available at 50 centimeters resolution. And we're very excited to have ICEYE and Capella Space partnered on our CLASI team. The goal of CLASI is to improve coastal air-sea measurements, particularly coastal winds. We are able to derive wind speeds from SAR using SAR wind retrieval algorithms to derive 10-meter wind speeds. These algorithms were used during the CLASI pilot, and we can also apply them to the 223 SAR images acquired during the 2021 field campaign. Here are examples utilizing Cosmos SkyMed SAR. An X-band SAR wind retrieval algorithm is applied, and we can resolve 20-meter winds. We can see that atmospheric features such as atmospheric gravity waves, wind shadowing regions, wind jets off the Santa Cruz Mountains, as well as diurnal variability through sea breeze fronts and land breeze fronts are resolved with high spatial resolution from SAR. We can also resolve oceanic features such as internal gravity waves. Note the strong wind gradients present within the coastal area of Monterey Bay. We have variability from 20 down to 5 meters per second in the 6-kilometer region near the shore. These gradients can be difficult for models such as COAMPS to resolve due to limitations in model resolution, as well as physics parameterizations. We can also apply these SAR wind retrieval algorithms to our new satellite constellations. Here is an example from ICEYE. We can apply an X-band SAR wind retrieval algorithm developed during the pilot to the CLASI 2021 ICEYE SAR image. And we can derive 20-meter resolution winds. So far, the results for the new SAR constellations are very promising, and we're excited for the future use of them. We can also dive into SAR feature tracking with CLASI. Here, an example of tracking atmospheric gravity waves during the pilot in 2016. Also, our PhD student, Samantha is working on feature tracking of internal waves using SAR imagery from the CLASI 2021 field campaign, and she will be discussing her techniques following on right after this one. In addition to wind products, air-sea flux products can be derived from SAR intensity images using the newly developed SAR land-air-sea transfer SLAS technique developed during the pilot. There are two parameterizations, SLAS-deep and SLAS-shallow methods that were developed in 2016. Here's an example of SLAS-shallow derived air-sea products, including SAR-derived ocean wavelength, SAR-derived phase speed of the waves, wind speed, wave age, surface roughness length, drag coefficient, and wind stress. These are all derived at 20-meter resolution. The SLAS-shallow technique is able to resolve diurnal variability from a sea breeze front shown in this example. Again, we can see the sharp gradient in these features in this less than 6-kilometer regime close to the coast in shallow water. SAR and NDBC buoy wind speeds were compared in deep water, and the correlations were on the order of 0.95, which are in good agreement. In 2021, there are significantly more in situ measurements for SAR validation, with the addition of 8 ACES buoys, as there were no buoys deployed in the pilot, and we have about 200 more SAR imagery. Therefore, we continue to explore the buoy SAR validation with the 2021 dataset. We also were able to organize co-located drone flights, small boat transects, and SAR image acquisitions during CLASI 2021 back in September. These collocations will be useful for mean wind speed comparisons. This is an exciting new addition for CLASI, utilizing ultra-high resolution Capella space SAR imagery at 50-centimeter resolution. Note that you can locate the drone and rib reflections within the SAR image, validating our collocations. SAR air-sea products are valuable for comparison with the Navy's COAMPS model. Here we have SAR and COAMPS derived wind speed, as well as surface roughness length. These outputs are useful to develop a coastal-aware COAMPS parameterization to improve coastal boundary layer forecasts. Overall, SAR and COAMPS compare well in deep water, and they are in less agreement in the shallow water regime, less than 6 kilometers from shore. Therefore, this is a region where COAMPS is focusing on the coast-aware parameterizations. Due to limitations in COAMPS's resolution, we can directly incorporate SAR imagery into higher resolution models such as LES. The SAR-derived sea breeze front that I mentioned earlier will be used as input into LES for simulation of the 3D coastal boundary layer and 3D winds. The sea breeze front is an example of an abrupt change in roughness from rough to smooth flow. After a famous micrometeorological experiment called the Bradley experiment in 1968, where measurements from anemometers were conducted over drag plates, mats of vertical spikes, and over a tarmac. Results included a step-like decrease in surface roughness over rough surfaces and a step-like increase in shear stress over smooth surfaces. With SAR, we have real-world observations of the sea breeze front or abrupt change in surface roughness present in the Bradley experiment. Therefore, we can use these observations from SAR of wind and surface roughness length over the ocean, derived using SLAS, and directly input them into LES, using them as initial conditions to run the model. Typically, simulated observations are used as initial conditions for LES within the literature. We can see a similar step-like increase from rough to smooth flow shown across the sea breeze front, which is in agreement with the Bradley experimental data. Ultimately, our LES output can derive 3D winds. Here is a contour of vertical velocity using SAR input directly. Bradley and LES simulations and LES-SAR results can be compared for rough to smooth flow transition. Our LES-SAR results are shown in blue and the Bradley experimental data is shown in the circles. Overall, they are comparable. LES-SAR changes in shear stress are within the range of the Bradley experimental data, but are slightly higher due to SAR observations originating over the ocean as opposed to land within the Bradley experiments. Future applications that I didn't have time to discuss here involve incorporating SAR and land-based radar comparisons, as well as SAR and aircraft atmospheric profiling. And there will be continued collaboration efforts with the in situ observation and modeling groups. Thank you, that's all I have. If you have any questions, feel free to email me. And thank you again to all my collaborators on CLASI.